Hello everyone, my name is Joey and my semester specialization is on earthquakes and how structures are designed to resist them. As is likely common knowledge, earthquakes are caused by the buildup of energy in faults when tectonic plates are prevented from moving. The release of this energy causes the ground to shake and move, the magnitude of the motion depending on the energy released. Roughly 27,000 people are killed every year as a result of seismic activity, and FEMA estimates that earthquakes cost the US $6.1 billion every year. However, since earthquakes are unpredictable in where and when they might strike, these are just average numbers. In 2000, there were only an estimated 231 deaths, whereas in 2010 there were 226,000, most of which came from a 7.0 earthquake in Haiti. Earthquakes have a few effects on soil, though the exact way that soil will react depends on the geotechnical parameters of the soil. One of the deadliest effects is liquefaction, which is where loosely compacted, water-laden soil loses its bond with itself, beginning to flow like a liquid. This also results in rapid loss in bearing capacity, which can cause rapid settlement and even topple buildings. The top right picture is from a series of earthquakes in Christchurch, New Zealand from 2010 and 2011, where the city experienced severe liquefaction that caused more damage than the actual quakes themselves. In 1964, liquefaction in Niigata, Japan toppled several apartment complexes. Another effect earthquakes can have is ground fissures, where the ground splits apart at a fault line. The bottom right picture is evidence of this from an earthquake in Ecuador. The last major effect I'll cover is slope stability. The shaking caused by an earthquake can trigger mass of soil to slip away from a slope, though the actual mass of soil that will fall depends on the magnitude of an earthquake, the failure type on the slope, soil conditions, how saturated the soil is, as well as the slope itself. Energy is transferred to structures from the soil using soil-structure interaction, which depends upon structure type and size as well as the type of soil. This transfer of motion causes a moment in the structure, which the walls of the structure must resist. This moment gets larger the taller the building is, becoming harder to handle. It can also cause horizontal and vertical movements. This can be during the shaking, where the structure is jostled with the ground's movement, but it's also possible that the shaking causes settlement or displacement of the structure, sometimes even by several feet. When structures are in close proximity to each other, like in cities, they can create an amplifying effect on the seismic wave, which can insulate some buildings as well as increase the damage to others. Smaller buildings near larger buildings tend to receive more stress as a result, but the amount depends on the structures as well as the distances between the two. The following are a list of some seismic resisting systems, but this is by no means all of them, only what I covered in my report. For smaller residential buildings, the wooden frames that they are built on work well to dampen the stresses in them. This works well for small earthquakes, but larger events will likely overtax the system and cause collapse. In larger structures, the wooden frames are replaced by heavy steel frames. Braced and moment-resisting frames will keep the structure rigid and prevent movement, but if they receive too much stress and start to deform, it will require the replacement of damaged components, often the complete demolition of the building. One way of increasing moment resistance in larger structures comes from an outrigger truss system, which connects the braced frames of the core to the perimeter of the building. This helps to reduce the total moment that the members experience, lowering the overall stress on the building. Large tremors will still cause deformations, but these can be planned into the design, allowing for specific members to receive the majority of the damage as well as being easily replaceable. The picture on the right shows how an outrigger looks on a design view. Another way of decreasing seismic load is the friction spring. One such model is shown on the right. It consists of concentric steel rings which slot into one another to provide a dampening effect. It sort of works like shocks on a car, but for larger loads. They expand and contract when under motion, which diverts some deformation to this motion and decreasing the load on the building. Another type of dampener uses a viscous fluid to resist motion. This works in a similar way to friction springs, but using the motion of the fluids instead of the metal rings. Pistons are a good comparison, with compressible fluid within that can absorb some of the load. It is possible to retrofit a structure to increase seismic resistance, which might need to be done if the danger of earthquake damage is reassessed to be higher than originally thought during initial construction. Depending on the building's situation, there are three main ways to go about this. Increasing the size of internal members is one way, but might not be feasible if there isn't enough room inside, or doing so would be too expensive. Installing more seismic resisting systems in the building might also be possible, but suffers similar constraints as increasing member size. There's also the possibility of constructing more rigid outlier structures and connecting them to absorb most of the energy, but this requires land to be available for them, as well as increasing the foundation they require. The last thing I'll cover is an advanced seismic warning system that the United States Geologic Survey, USGS, is constructing for the West Coast. Called Shake Alert, once an earthquake is detected, it will send an alert to warn residents of an impending earthquake. However, this warning could only be in the range of seconds to little over a minute, as earthquakes travel quickly. It also takes time to be able to tell the magnitude of an earthquake, as well as sending messages to thousands or millions of inhabitants. Even then, if you happen to be over the epicenter, you still have little to no warning. Earthquakes are dangerous environmental hazards, especially because of how unpredictable they are. In order to protect ourselves against them, it requires the conjunction of multiple engineering fields. Geotech describes the state of the soil, structural engineering for how structures react, as well as mechanical engineering for the design of dampening devices. The design and maintenance of these systems is vital to saving lives in earthquake-prone